Welcome to This Explainer. I am incredibly excited you're here because today we are going to dive into the raw, bizarre, and absolutely staggering power of Earth's geology. When we think of volcanoes, we usually picture pure devastation, right? Like a force of nature that levels landscapes and darkens the sky. But what if I told you that the very engines of destruction deep within our planet are actually the master architects of its surface and potentially the grand creators of life itself? Get ready, because we are going on a huge journey today, starting from the deepest, hottest magma chambers all the way to the most extreme environments on the planet. Now, I want you to just stop and consider this question for a second. What could possibly connect a vigorously shaken bottle of soda to the very origins of life on our planet? It sounds kind of wild, like a riddle, I know, but by the end of our time together today, you're going to see exactly how these two seemingly unrelated things are intimately bound together by the exact same forces of physics and chemistry. Prepare to completely rethink your definition of a natural disaster. Okay, let's get right into it by exploring the engine that drives all volcanic activity: magma. To figure out why volcanoes erupt the way they do, we first have to understand viscosity. Viscosity is simply a liquid's internal friction, basically its resistance to flow. Just think about the difference between pouring a glass of tap water and pouring a jar of thick, cold honey. That difference in how thick and sticky versus thin and runny a liquid is, that dictates whether a volcano is just going to gently ooze lava or violently detonate. So, what actually makes magma thick or runny? Well, it comes down to its chemical composition, specifically its silica content. Now think of silica molecules kind of like strands of spaghetti. Seriously, in low silica magma, the strands are really short. They flow past each other super easily, creating a fluid, runny lava that results in relatively quiet, gentle eruptions. But in high silica magma, those spaghetti strands are super long and complex. They tangle and knot together, creating an incredibly thick, sticky magma. And as we're about to see, when you combine that sticky, tangled magma with massive heat and pressure, you are setting the stage for a total explosion. And hey, this brings us right back to our soda bottle. Deep underground, magma contains all these dissolved gases, mostly water vapor and carbon dioxide, which are kept in a liquid state by the crushing pressure of the Earth above it. But as this magma rises towards the surface, that pressure drops. The gases separate from the liquid and form bubbles. This is a process called gas exsolution. If the magma has low viscosity, the bubbles simply rise and escape, kind of like opening a normal soda. But if you have that thick, highly viscous, tangled high silica magma we just talked about, the bubbles are trapped. The pressure just builds and builds as the gases expand, exactly like a violently shaken soda bottle, until the magma literally shatters in a cataclysmic, explosive eruption. To really put the scale of this planetary pressure cooker into perspective, take a look at this number. Right now, there are approximately 1,350 potentially active volcanoes worldwide. 1,350. And actually, scratch that. That doesn't even count the countless vents hidden deep under our oceans. Our planet is incredibly active. It's essentially this giant, breathing engine that's constantly churning, melting, and reshaping its outer crust through a massive, interconnected volcanic network. All of this brilliantly illustrates how these different magma types, varying viscosities, and intense gas pressures don't just determine how an eruption happens, but what is left behind afterwards. Over time, these dynamic forces actually construct four distinct structural shapes right on the Earth's surface: cinder cones, composite or stratovolcanoes, shield volcanoes, and lava domes. Each and every one tells a totally unique story about the exact magma that built it. Let's break down the first two real quick. Cinder cones are the simplest. They form when gas-rich basaltic magma is just blasted into the air, cools rapidly into these bubbly rocks called cinders, and piles up in a neat steep cone around a single vent. Simple enough, right? On the total opposite end of the spectrum, we have shield volcanoes. These are massive, broad mountains with super gentle slopes. Think of the ones that make up the Hawaiian Islands. They're built slowly, layer by painstaking layer, by thousands of fluid, low-viscosity lava flows that spread out over huge distances before they finally cool. Then we have stratovolcanoes. These are those grand, classic, steep-sided mountains you see in pictures, like Mount Fuji or Mount Rainier. They're built from alternating layers of lava flows, ash, and volcanic rocks, very often resulting from highly explosive eruptions. And finally, we have lava domes. Remember that incredibly thick, sticky, high silica magma? Well, sometimes it is just too viscous to flow at all. It literally just squeezes out of the vent and piles up like a giant, rocky muffin. And these are incredibly dangerous because as they grow, their cooler outer layers can shatter, sending terrifying avalanches of scorching rock and gas racing down the side of the mountain. Bizarre extremes, Kawah Ijen volcano. Over on the island of Java in Indonesia, you'll find an environment so incredibly bizarre, it literally looks like it belongs on another planet entirely. Nestled right in the Kawah Ijen crater is a breathtakingly beautiful turquoise lake. But do not let that inviting color fool you for a second. This is actually the world's largest highly acidic lake, boasting a shocking pH as low as 0.5. To put that into perspective, battery acid has a pH of about 0. The water gets its mesmerizing color from an extreme concentration of dissolved metals and a continuous inflow of hydrothermal waters completely charged with toxic volcanic gases from the magma chamber below. It is utterly beautiful for sure, but deeply, deeply deadly. And right next to that giant acid bath is a phenomenon that is just mind-blowing. Kawah Ijen features an active solfatara, which is a volcanic vent that continuously emits hot sulfurous gases. When these superheated gases emerge and hit the oxygen-rich atmosphere, they spontaneously ignite. They burn with this intense electric blue flame that illuminates the entire landscape at night. Some of the gas even condenses into a molten liquid sulfur that flows down the rocks, still burning with that exact same ethereal blue fire. But here is the really wild part. This extreme toxic environment isn't just a geological curiosity, it is a workplace. Artisanal miners navigate the steep, incredibly treacherous paths of the caldera, braving poisonous, choking sulfur dioxide gases to manually extract that condensed, solidified sulfur. Using just basic tools, they break off chunks of the yellow mineral, pack it into baskets, and carry loads that often exceed their own body weight. We're talking up to 200 pounds lugged out of a toxic crater. It's just a stark, humbling reminder of the human element operating right on the extreme fringes of Earth's geological power. The spark of life. Volcanic lightning. Okay, so we've seen the toxic, the bizarre, and the dangerous, but now let's look at dirty thunderstorms. These are colossal electrical storms generated entirely by the sheer brute force of volcanic ash columns. When a highly explosive volcano erupts, it blasts billions of tiny, shattered rock fragments, ash, high into the stratosphere at supersonic speeds. As this super-dense plume rapidly expands and violently churns, those tiny grains rub and collide against one another. This intense friction creates massive static charges within the ash cloud. The positively and negatively charged areas separate, and when the difference becomes too great, boom, the energy discharges. The result is a ferocious web of crackling volcanic lightning illuminating the dark eruption cloud from within. It is truly nature at its most dramatic. So how on earth does a giant lightning storm in an ash cloud tie back to our very existence? Well, back in the 1950s, the famous Miller-Urey experiment demonstrated that if you take the gases present on early Earth and introduce electrical energy, you can actually create amino acids, which are the fundamental building blocks of life. For a long time, scientists wondered where those exact conditions could have existed naturally. The answer? Primeval volcanoes. They emitted the perfect reducing mixture of gases, like ammonia and methane. They vented vital water vapor, and through those dirty thunderstorms, they provided the massive electrical sparks needed to synthesize complex organic molecules right out of inorganic matter. It totally flips the script, doesn't it? We started out by looking at the destructive potential of magma, the explosive power of gas, and these incredibly extreme toxic environments. But through that exact same intensity, volcanoes sculpt the continents, they fertilize the soil, and, quite possibly, they provided the primordial spark that ignited life itself. So, I'm going to leave you with this. If these colossal planetary engines hold the power to destroy, could they also be the very reason we exist to witness them? It is such a beautiful, humbling thought. Thank you so much for joining me on this explainer, and I highly encourage you to keep questioning and keep exploring the absolutely incredible world right beneath our feet.